Hello and welcome to the summary video of the first lecture of Structural Equation Modeling 2, Structural Equation Modeling. In this lecture we're going to expand the framework from SEM1, the Confirmed Effect Analysis Model, to actual Structural Equation Modeling. And before you watch this video, I can recommend that you watch the video on expectation algebra and covariance algebra. Because it's useful to understand some of the concepts that I talk about in this lecture. So in structural equation modeling, we make a distinction between two types of variables, exogenous and endogenous variables. And they have some different names as well. So exogenous are also called independent variables sometimes, endogenous are also called dependent variables sometimes. You can also think of endogenous variables as outcome variables. So exogenous variables are variables for which the causal origin is not modeled, which basically means that they don't have incoming arrows in the path diagram. So we have no model for exogenous variables, they're just there. They have a variance, they have a covariance. We don't aim to explain these variances and covariances, but we use these variables to explain the endogenous variables. So typically these are termed x. X is also used for indicators of a latent variable. And you might see that in CFA all the latent variables were actually exogenous latent variables. So we did not explain the latent variables themselves, except in the last lecture when we went to higher order models. The latent variable is sometimes called xi. Sometimes you'll see that, especially in older papers. Now an endogenous variable is a variable for which the causal origin is modeled, which means that there's an incoming arrow, and that means that we are not modeling a endogenous variable that has a variance itself, but we are going to explicitly model where every part of the variance comes from. So endogenous variables, they don't have a variance or covariance themselves, but they are composed of variance of covariances of exogenous variables. And then you can also see a residual as an exogenous variable. Now the aim of structural equation modeling is to explain the variance and covariance between all endogenous variables. Now one way to do that is by drawing these kind of path models. This is known as path analysis. And that's a form of structural equation modeling. I'll show you at the end of this video also how you can do that in a SEM framework. And you can think of this also as structural equation modeling. So here I have three path models, or SEM models. They consist of exogenous and endogenous variables. So the exogenous variables here are labeled x. So we have x here, we have x1 and x2 here, and here we have simply 1x. And the endogenous variables are labeled y. So in this case here, we have two endogenous variables. They're both caused by this one exogenous x. Typically we don't draw the variance anymore of exogenous variables. You also saw some path diagrams in CFA where you did not draw the variance of the latent variable. Because they are exogenous, they have a variance, and you don't need to explicitly say that as well. So typically we ignore them, but we do draw all the paths and all the residual variances from the endogenous variables. And this is really the goal of SEM. And it's also what we've been doing already in CFA modeling. We had an exogenous latent variable for every latent variable we want to model, and our indicators were endogenous, and we want to model their variance and covariance structure. So here's a bigger example of a path model, which has 1, 2, 3, 4, 5, 6, 7 variables. So that means you have 28 observed variances and covariances. In SEM2 we can ignore the mean structure again for the most part, because it's not that relevant. You can add the amount of means here, but you can also add the amount of intercepts here. That always cancels out. So I'll just talk about variances and covariances. So we have 28 observed variance and covariance. We're going to model it with this theoretical model, where we have two exogenous variables, a and b, and they are correlated, and they have a variance. We always allow exogenous variables to be correlated as well. It would be weird not to, because you kind of expect everything to correlate with everything. And all these others, C, D, E, F, and G, are endogenous variables for which we try to explain variance. So they have a residual variance, that you see here, and they have incoming arrows. Now in this model, we have 7 regressions, 1, 2, 3, 4, 5, 6, 7. We have 7 variances, 1, 2 exogenous variants, and 1, 2, 3, 4, 5 residual variances. We have 1 covariance between these 2 exogenous items, and that leads to 15 parameters. So that means we have 13 degrees of freedom, and we can fit this model exactly the same way we've been fitting CFA models so far. Now for that we need to know the implied variance covariance structure of this model. And to do that we can use the expectation and covariance algebra we learned in the previous video lecture. So we can do that. We can do that for every pair of variables. We can compute the implied variance between A and B, A and D, A and F, A and G. It's just quite a lot of work, especially if we use univariate variance covariance algebra. Luckily, there's also an easier way to do this. There's something called Wright's path tracing rules, and I'll explain it in more detail in the lecture. But it's an easy way to use the path diagram to arrive at the same implied covariances and variances, which is really nice. The idea is that if you want to have the covariance between 2 variables, like f and g, we can first trace arrows backwards, so we go against the direction, until we find one double-sided arrow, which you can think of then as a U-turn in the track. And from that point we go forward until we reach the variable of interest. And we can do that for a covariance or variance. So from f we can go backwards, take this U-turn here and go forwards, for example. And then what we do is we just multiply all the parameters we encounter on the path. And then for every possible path we do that, and then we add all combinations of that. So for f and g, we want to know their covariance. We start at f. We can also start at g and go to f. It doesn't matter, it's the same result. But let's say we start at f. We can first trace the paths backwards, so we go backwards to C, so we encounter E here, that parameter. We go backwards here to A, then we take this double-sided U-turn, and from that point we go forward to variable E, and we go forward to G. And now we encounter the parameters E, A, H, D, and G, so we multiply them. That's this last part here. But there are more ways to go from F to G. So we can also go from F via D, A, B, E, G. So then we have these parameters here. And we could also go from F to D, from D directly to B, then take this double-sided arrow at the variance, which you have to remember is sometimes not drawn, then go from B to E, and then from E to G. And then we have the path f, this parameter here, times c, this parameter here, times the variance of b, times d, this parameter here, times g. And if you do the covariance algebra for f and g, you will get the exact same result, which is really nice. So this would actually be really complicated to do in covariance algebra, but now it's pretty easy. It's a nice way to simply look at the path diagram and think about what does it imply in terms of variances and covariances. Now this is still a bit hard to do for every variable, and there's an even easier way, and that is again by using matrix algebra. So here I define a SEM model, and this is actually known as the all-y SEM model, and that's because I am treating exogenous variables as endogenous variables, which mathematically doesn't really make any difference, but it makes the notation a bit different, and then this psi matrix here is the variance covariance matrix of the residuals. So that means that here we are modeling exogenous latent variables as something as a residual. That doesn't really matter mathematically, but that's why we call it an all-y model. Sometimes you see an extended model as showed in the lecture, and it has like twice as many Greek letters, and there's really no reason to do that. So here we have y, we have our well-known measurement model, y equals lambda times eta plus epsilon. But now we also have a model for eta itself. So eta equals beta times eta. And this beta matrix contains regressions. And parameter actually in column j and row I will mean that variable y will cause I. So it's a transpose of a directed network, which is something you have to take into account. Types itself, but because this beta is not fully populated, so it will have many zeros, you won't actually regress an individual element of eta on itself, but you will regress different parts. This is a vector, might have 3 variables in there, and you might use this beta to model that the first variable will cause the second one, so not causing itself, plus this residual. Then we can rearrange this term as seeing as eta equals an identity matrix minus beta, that inverted, times this zeta. Now with this expression we can do our variance covariance algebra. You see it on the bottom here. There are some steps involved, but in the end we get to this expression here, where we have lambda times an identity matrix minus beta inverted, times psi, times identity matrix minus beta inverted transposed, times lambda transposed, plus theta. And here it's important that psi here contains both variance and covariance of exogenous latent variables. So a block of it will have all variance and covariances, and another block of it will simply be diagonal because it will be the residual variances of endogenous variables. We don't want to model correlations between endogenous variables unless we really have to. So it will look a bit weird, but usually the software will do that automatically for you. So this is the big SEM expression, and actually this is pretty much the same that you saw in CFA with the addition of this beta matrix. And if beta is 0, which is the case in the CFA model, then this will be an identity matrix. The inverse of an identity matrix will be an identity matrix. So then this just drops out and we get lambda times psi times lambda transpose plus theta. So it's pretty much a generalization of the thing we've already been working on for a month now in SEM1. And this is how we fit the SEM model. We do the same thing. We do the same fit measures. We do the same optimization algorithm. So everything that applies, that you learned in SEM1, applies for SEM modeling as well. We just have one extra matrix, which means that the sigma is a bit more complicated, but all the rest applies. The degrees of freedom applies, the fit measures applies, the way we compare models applies, nesting relationships applies. So you pretty much already know SEM. So here's a path diagram model where x causes y causes y2. This we could model in SEM, but often the software doesn't allow you to specify this. It only allows you to work with these latent variables because it tries to optimize this expression. And to do that, we can use a trick. We can represent every observed variable with a latent variable that has no measurement error. So this factor loading set to 1, there's no measurement error. So eta1 just simply is y1 here. And with this trick we can use our SEM model to model any causal effect between observed variables as well, by modeling them as dummy latent variables that just indicate the same parameter. You can see here that I'm modeling this eta to have a residual variance, which is this all y notation, but just the same as having a variance. So this model will allow us to test this hypothesis that eta1 causes eta2 and eta2 causes eta3. Or you could see that eta2 is mediating the effect from eta1 on eta3. And the model matrices for this are lambda, which is an identity matrix, psi, which is diagonal here, because only eta1 is exogenous, and the rest are endogenous, theta, which simply has zeros, and beta, which has these two beta values here. In Lavaan, the code for this is really easy. You just use this tilde operator, which is the same that you already use in the LM function or the GLM function. So the Lavaan model just extended with this tilde operator is SEM. And you have to use the SEM function, not the CFA function for that. But otherwise it's all the same. And then we can do more advanced things. So for example, here I have all the latent variables indicated by 2 indicators, where I've set the scaling. But then the model is identified, and I can actually estimate these residual variances. I can estimate this factor loading. It's only identified because there's an effect here, of course. Otherwise you need 3 indicators. And this allows us to test some hypotheses on these latent levels. So the Lavaan model for this is very simple. This uses the SEM function, not the CFA function. It's pretty much the same. And the model is pretty simple, just is eta 1 is indicated by y1 and y2, eta 2 is indicated by y3 and y4, and eta 3 is indicated by y5 and y6. They add these two regressions, and then Lavaan will do everything else for you. Okay, that's it for this summary video, and I'll see you all in the lecture.